Okay, so we're going to be looking at area and arc length in polar coordinates. And just a reminder, um, when we're talking about area, we're going to be finding areas of little circles. Not circles so much, but sector of a circle. And just a reminder, if you have a circle, here's your circle right here, and here's some sector. The way we find that area is we note that if this has angle theta, there's going to be a relationship between theta and the full angle in a circle, 2 pi radians, and that ratio of theta to 2 pi is going to be equal to the area of my sector over the area of a full circle, which is pi r squared. And when we solve that for area of the sector, the pi's are going to go away, and we're going to get 1/2 theta r squared. That'll tell us the area of a sector. Okay, so using this, let's think about how to find the area um, that's swept out when we're talking about polar coordinates. So here we have our function, um, and let's consider this area here to be an area of a sector. So we're going to call that angle d theta. It's a very small change, and as long as it's a very small change in theta, even though this doesn't look totally circular here, it'll be approximated as a circle. So the idea is, when we're at some position and when we have some little change in d theta, that is, it's sweeping out a sector, and we can find that area of the sector. So the area of a sector, using this equation that we just found or remembered, instead of like A, let's say dA, because it's a little small area, and that dA equals 1/2, and instead of theta, it's a little change in theta, so d theta times r squared. But we want to have, there needs to be the same variable r and theta, so we can express, since we're talking about polar coordinates, we can express r as a function of theta, because r depends on theta in polar coordinates. So therefore, our little dA equals 1/2 f of theta squared times d theta. And then all we need to do to find out the whole area swept out from some theta equals alpha to theta equals beta, we're just going to integrate from alpha to beta 1/2 f of theta squared d theta, and that'll tell us the whole area over some given range. Pretty straightforward. So let's think about an application. Let's find the area of the region bounded by this cartoid. And cartoid is something that we looked at before. Remember, it's shaped like a heart. So what we're going to do is we're going to integrate from 0 to 2 pi and what we're going to be integrating is using that equation that we just looked at, that we have 1/2 f of theta squared, or r squared, d theta. Now it's a matter of expanding and doing some integration. So let's do the work here. So 0 to 2 pi. I'm pulling the 1/2 out in front for right now. Four plus 8 cos theta plus 4 cos squared theta d theta. And then what we need to do is use this hint that they gave us so that we could rewrite this 0 to 2 pi 1/2 4 plus 8 cos theta plus 4 times 1/2 times 1 plus cos of 2 theta. Okay, so now we need to do a bunch of simplifying, but just integration here. And what I'm going to do, pause the video and kind of do a couple steps ahead so that you don't have to watch all this, the development for the simplifying. Okay, so that line that we just did just expanded that left-hand side, or sorry, the right-hand side. So now we can actually do the integration. So 4 integrates to 4 theta, 8 cosine theta becomes 8 sine theta plus 2 theta, and the integral of 2 cosine 2 theta is just sine of 2 theta. And we're integrating from 0 to 2 pi. Well, putting 0 and 2 pi in for sine is going to turn both of these to 0. And when I put 0 in for theta, it goes to 0. So this ends up just being 1/2 times 4 times 2 pi plus 2 times 2 pi. And that simplifies to 6 pi units. So that's the area of the cartoid, and we found that area using the fact that a little chunk of area equals 1/2 f of theta squared d theta, and integrating it from 0 to 2 pi. Okay, so more, now what we're doing is we're going to look at arc length. So we looked at area, now we're going to look at arc length in polar coordinates. And a couple things that we need to remember from parametric equations, from polar coordinates, is that x equals r cos theta, y equals r sine theta. So therefore, since r is just f of theta, we could rewrite this. And what we remember from arc length is that arc length is, this looks similar to how it looked for parametric equations. So arc length is dx d theta squared plus dy d theta squared, d theta. And what we want to show, what we want to get is an expression. We want to simplify this expression. So if we think about what dx d theta is, using this, because of the dx d theta using the product rule is going to be f prime of theta times cos of theta plus f of theta times minus sine theta. Okay, and dy d theta is going to be very similar. Dy d theta is f prime theta times sine of theta plus f of theta cos of theta. And then what we need to do to find L is square them and sum them up. And when we square them, let's actually do this work on another page. So hold on one second. So now we're going to simplify those. So we're gonna get dx d theta squared. Dx d theta squared is going to be f prime of theta squared times cos squared of theta plus f of theta squared times negative sine of theta squared, so the negative is going to go away. So just sine squared theta. And dy d theta squared equals f prime of theta squared times sine squared of theta plus f of theta squared times cos squared of theta. And what you're hopefully seeing is that you're like, trig identities, sine squared plus cosine squared equals 1. So just going back, remember, arc length equals the sum of the square root of dx d theta squared plus dy d theta squared d theta. And so if I add these up, when I add these up, just adding vertically, if I were to, since I could factor these two out, and I'm left with just cosine squared plus sine squared, well, that's 1. So this ends up just being f prime of theta squared plus, and if I factored f of theta squared out, what I'd be left with is sine squared theta plus cos squared theta, same thing, equals 1. So plus f of theta squared. So what we're left with is just, f prime of theta squared plus f of theta squared. And that's this chunk right here. So therefore, we can get an expression for L, and the expression for L, our arc length, is just the integral expression for L would be the integral of the square root of f prime of theta squared plus f of theta squared d theta from alpha to beta. Pretty pretty nice. It's just the derivative squared plus the function squared, square rooted. Uh, okay, so let's look at an example of that. Right here, we've got the logarithmic spiral, r equals e to the theta. And you get this cool spiral that you can see um, graphed already right here. And what we want to do, this is graphed on the interval from 0 to 2 pi. We want to find the length of this line, the length of this logarithmic spiral. So what we need to do to find that, we know that our function, we know that f of theta equals e to the theta. And we know that f prime of theta, well, taking the derivative of that, the derivative of e to the theta is just e to the theta. So the arc length of my spiral will equal the integral from 0 to 2 pi, the square root of e to the theta squared plus e to the theta squared, which equals sigma, or sorry, the integral of from 0 to 2 pi square root of 2 times e to the theta squared. And I should have had a d theta here and a d theta here. Well, this is going to, this actually integrates quite easily because of the nature of the e to the theta. So what we end up getting when we do this integration, we can separate it. So we have the square root of 2 times the square root of e to the theta squared d theta. And this chunk here, this bit here, because we've got square root and something squared, we could re-express that as pulling the root 2 out in front, the integral from 0 to 2 pi of e to the theta d theta. Okay, well, e to the integral of e to the theta, love working with e to the x or e to the theta. The integral of e to the theta is just e to the theta, and we're going to evaluate it from 0 to 2 pi. And being careful to know that at 0, e to the 0 is not 0, rather it is 1. We can evaluate this definite integral, and we get that it has an arc length of root 2 times e to the 2 pi minus e to the 0, or just 1. And this is our arc length of the spiral, the logarithmic spiral, and we found this using that equation for arc length in polar coordinates. This is just a bigger picture of that logarithmic spiral, and we went ahead earlier and found that length. And that's it. So there's really just two things two things to take away from this. If we're talking about polar coordinates, so we've got polar coordinates, and we've got in terms of theta comma r. If we want to find the area in polar coordinates, the area equals the integral of 1/2 f of theta squared d theta. And if we want to find the arc length, that's what we just did. If we want to find the arc length, it's just the integral of the square root of f prime of theta squared plus f of theta squared d theta. Those are the two main topics. That's it.